So here's a great example of a paired t-test problem. Let's first talk about why we know it's a paired t-test problem. So the first question we ask ourselves is always, is this data quantitative or is it categorical? And reading this little paragraph that we see here about the actual study, we see that we have oocytes from each of 4 female frogs divided into 2 batches. The batches were exposed, and at the end, they assayed each batch for CMP content with the results given in the table on the next page. But before we even look at the next page, we can already know that this is quantitative data because they are measuring a certain amount of content for each batch of oocytes. So they're not just counting the number in different categories, they're measuring. So this is quantitative data. And not only that, we see that we have paired data for sure because they're taking these oocytes from each of 4 females. And so each female produces a pair of observations, some oocytes that were exposed to progesterone and some that were not. And then here's what the data actually looks like. There are 4 frogs. That's 4 pairs of observations, where each pair represents measurements on the same frog, or on oocytes from the same frog, but under different conditions, the control and the progesterone conditions. And in the table, we already see that they've already calculated the difference in those 2 measurements for each of the 4 frogs. The other thing to notice here is that we've also got a row for the mean and the standard deviation. So what we care about is the mean and standard deviation of the differences. So it's this and this that we're actually going to use to formulate our test statistic. This quantity here is the mean of the differences. So we can write it as d bar, and this one is the standard deviation of the differences, so I'll write that as st. So because we have quantitative data that's set up in this paired way, that's making us think we're going to use a paired t-test. Now, one thing I should mention here is for a paired t-test to work, you must be able to assume that the underlying data is normal, and that's not stated anywhere in this problem. However, we're going to go ahead and add a little addendum here and assume that the data is normally distributed. So I'm writing this here kind of as part of the setup of the problem. Assume the data is normally distributed. And just so you guys know, on a test, I'm going to tell you that clearly, whether you can assume that or not. But they didn't really make it clear enough here, so that's what I'm doing for you guys. So because we have normally distributed data, even though it's a small sample size, we only have 4 pairs, we're going to be able to use a paired t-test. So here's how it works. First of all, stating the null and alternative hypothesis is pretty easy for a paired t-test. The null hypothesis is just that the population mean of the first group is equal to the population mean of the second group. The alternative hypothesis is that they are different. The next step is making the test statistic. So the test statistic in the paired t-test looks like this. Test statistic equals d bar over the standard error of d bar. And then the standard error of d bar is just the standard deviation of the pairs, so that's here, divided by the square root of the number of pairs. So this is going to be 0.4 divided by the square root of 4, which is 0.2. So now, between having calculated this standard error of d bar and knowing d bar is 0.68, as I see here, then I can now actually work out my test statistic, which is going to look like 0.68 divided by 0.2, which is 3.4. We will take that quantity to the t-table, but before we do that, we need to know what the degrees of freedom are, and when we are talking about paired data, the degrees of freedom is just going to be the number of pairs minus 1, which here is 4 minus 1, which is 3. So I've written the test statistic here with the degrees of freedom, and a side comment I'll make before we actually go to the table is when you look up this value 3.4 or whatever it is in the t-table, you should be looking up the absolute value of the test statistic you got. So if I had gotten a negative test statistic here, I would want to just be using the positive version of that to get the upper tail probability. So here I've pasted in the t-table, so we can, it's just the first few lines of the t-table, but that's all we need because we only have 3 degrees of freedom. So that means we're looking at the third line here, where degrees of freedom is 3. And then I have my test statistic, it's 3.4, so I'm finding where it belongs on this row. And actually it was indeed 3.40, it was computed exactly that way. So I can say for sure that it's going to be somewhere between these two values on this row, which means the corresponding upper tail probability is between 0.02 and 0.025. So 0.02 is less than the upper tail probability, which is less than 0.025. Now, this isn't yet a p-value necessarily because we need to think about whether we're considering both tails of the distribution or just one tail of the distribution. If it is to be a non-directional t-test, then we need to take these quantities on the two sides of this interval and multiply by 2 because the table only shows us the probability for the upper tail. If we want to include both tails, as we need to do in a non-directional test, then we'll multiply by 2. So because our null hypothesis looked like this, mu1 equals mu2, and our alternative looked like this, there's no directionality there, so this is a non-directional test. And so therefore I am going to say, okay, I need to multiply these probabilities by 2. So I have 0.04 is less than the p-value. What I'm ending up with here is the p-value. So we can see that the p-value is going to be somewhere between 0.04 and 0.05. And if we are using the typical level of significance, alpha equals 0.05, then we do have that our p-value is less than alpha, which means we should reject the null hypothesis. There is evidence that the two population means are different. So we can say there is evidence that the average CAMP level is different among frog oocytes treated with progesterone compared to those that are not treated with it.